Hello everyone, my name is João and I'm here to present the paper named Redundancy Resolution Integrated Model Predictive Control of CDPRs, Concept, Implementation and Experiments. The authors of this work are Chemori, Gouttefarde and me. First, I would like to address the context of the project on which this work has been developed. The European project named Hephaestus presents as main goal the design and construction of a robot able to perform the installation of curtain wall modules in a building facade. As you can see in this figure on the left, we depict a CAD view of the CDPR that is responsible to take the curtain wall modules on the ground and install them on the building facade. On the figure on the right, you may see the constructed prototype. In order to better illustrate the elements of the project Hephaestus, I would like to share with you this video. You can see that a key element is a cable-driven parallel robot constrained by 8 cables. 4 of them present their drawing points positioned on the upper part of the building, and the remaining 4 present their drawing points close to the ground. Therefore, this is a fully constrained CDPR. You also can see some other elements. Each drawing pulley is equipped with a force sensor that is used to monitor and control the cable tensions. We highlight that the system is controlled with the software TwinCat from Bakeoff. This is a software typically used in the industry. We will see that this was an important constraint considering this work. And these are our partners. Having an overview of the project Hephaestus, we can address the specific problem considered in this paper. We are focused in the development of advanced control techniques for the position tracking during the curtain wall module installation. Before addressing the control methods themselves, we should clarify the specific concerns related to the position tracking in the Hephaestus project. Firstly, since the CDPR operates in the front of a building facade, we have a reduced area available to the installation of the structure. As an illustration, considering that this red volume is the necessary workspace and that this other green volume is the workspace obtained in the design, we can see that the margin within the workspace devoted to uncertainties is rather small. Moreover, the robot should be installed in an uncontrolled environment, a construction site. Therefore, it may be exposed to large disturbances such as the wind. Similarly, safety receives special attention since we have a large payload, much more than 1 ton, handled in a construction site. In summary, these are some of our main concerns. In order to clarify the reasons that led us to the development of an MPC algorithm, we need to understand a characteristic that is typical on the state-of-the-art control schemes of CDPRs. Most of the published studies addressing this subject propose control strategies that can be summarized with this scheme. We will be focused on 2 key elements of this scheme. First, the main controller is responsible to define a range to be applied on the platform based on the comparison between the desired states and the estimations of the actual ones. Several control strategies have been used to this end. Similarly, for redundant CDPRs, the output of the redundancy resolution block is a set of cable tensions within the interval of admissible cable tensions that generates the desired range defined by the main controller. As illustrated in this animation, even if we have the incidence of disturbances depicted as this black arrow here, the control schemes discussed in the previous slides are able to define a range counteracting the disturbances and leading to an optimal cable tension, this red ball, within the intersection of the cube of feasible cable tensions and the plane define the vectors T that generate FD. Nevertheless, if for some reason, during the construction of the CDPR, the drawing points are not positioned where it should be, as illustrated here, and the presence of disturbances is too large, the desired range defined by the main controller may be unfeasible. Or more precisely, this plane do not intersect this cube, and this is indeed an empty set. More important than that, what is the output of the controller in this situation? Well, in practice, the robot suddenly stops in this case. Analyzing better this problem, This issue comes from the fact that the desired range is computed without considering the constraints related to the cable tension limits. In summary, the main causes of this problem may be that the desired range violates the workspace limits, perhaps because of errors on the construction of the robot or changes on the payload, and excessively large disturbances. The consequence is the sudden interruption of the robot operation. Revisiting the main concerns considered in this work, it's clear that this is a major issue. We don't have room for large uncertainties regarding the designed workspace, and we may be exposed to significant disturbances. Obviously, suddenly halting the motion of a platform of more than 1 ton would lead to safety issues. So this is our main problem. The solution of this problem would be to integrate the tension distribution algorithm within the main controller. Fortunately, this can be done using model predictive control. Indeed, model predictive control is one of the few control strategies able to handle system constraints explicitly. In this paper, we propose an MPC scheme able to handle the constraints of cable tensions as an integral part of the main control. The proposed MPC may be briefly described as follows. A linear discrete time model is obtained as an approximation of the well-known continuous dynamic model of a general CDPR. The recursive application of such model leads to a prediction of the future pulses and velocities within an interval of time denoted as prediction horizon. With that, for a given sequence of control inputs, a functional cost estimates the developed performance according to the desired behavior of the robot operation. In this work, we would like to minimize the magnitude of the cable tensions, the variation of cable tensions, and the tracking error. The minimization of this functional cost subject to the cable tension limit constraints is an optimal control problem that may be written as a quadratic programming optimization problem. The optimal solution is obtained using an algorithm based on the active set method, leading to the optimal control sequence. The first set of this sequence is applied during one sampling period, and the whole procedure is repeated for the next sampling time, characterizing a feedback control scheme. When this work was developed, the fastest prototype was not ready for tests. For this reason, a prototype with similar characteristics was used in order to perform the experimental tests. The next video is a short version of the video attached to this work. In order to illustrate this discussed characteristic of the proposed MPC, we address different scenarios using the same desired trajectory. First, we present a scenario using the cable tension limits of 100 and 400 newtons. You may see that the trajectory is successfully tracked with satisfying results. In comparison, we present the case applying a maximal cable tension of 260 newtons. The desired trajectory cannot be performed with this new set of cable tension limits. Even though the proposed MPC is able to track a trajectory as close as possible to the desired one without violating the cable tension limits. It is interesting to compare these two scenarios simultaneously. Here, I remind that the control scheme has been implemented in the industrial software TwinCAD. Since this software is not compatible with commonly used mathematical libraries, the control scheme has been implemented from scratch. Finally, the last scenario is performed with a state-of-the-art control scheme. We can verify that the sudden interruption on the robot operation takes place as discussed earlier. Thank you very much for your attention. I will be glad to answer any question you may have.